Hello, and thank you for joining. In this short talk, I will share with you how my colleagues and I designed our massive open online course Introduction to Aerospace Structures and Materials to be more than learners just listening to a talking head in front of a PowerPoint presentation, as is often the case. Our aim is to inspire you to engineer your courses such that the students will have a richer experience, mastering the subject of materials engineering. A subject most of us are very passionate about and would like to share with our students. When we talk of online learning, we often mean something different. What we really mean is that we are engaging in distant or remote learning. It is my view that distant or remote learning isn't equal to online learning. In fact, in my view, online learning, or rather using online tools to facilitate learning, is only a part of learning remotely. Let's face it, we all know that sitting behind a computer screen all day watching videos isn't healthy or productive. Don't we tell our kids off all the time? So why are we making our students do it? Secondly, were we not actively engaging as engineering education community to move away from long lectures with lecturers dispensing information and students not necessarily receiving said information, let alone process it? Thirdly, we want our students to stay on track. Studying on your own without any framework or structure can be very hard. If you combine this with the fact that engineering is also very much a hands-on degree, and the area of structures and materials engineering even more so, it stands to argue that these topics should simply not be taught by just watching video lectures. We want students to know about materials, how to use them, and how to design structures from them. Taking all this into account, we came up with the following approach. To provide the necessary structure in the course was designed to consist of 7 distinctly weekly modules, each having a similar structure and setup. Each model is examined with an online exam and a design assignment at the end of the module. The aim is for students to complete a module per week, spending about 6 to 8 hours on a weekly module. After completion of a module, learners are awarded an online badge and students need to earn 6 out of 7 badges to qualify for a certificate. We use badges as a progress marker as they've been proven to be a great motivational tool to maintain student engagement. As this is an engineering MOOC, we felt we should aim to give students similar opportunities as we would our on-campus students, where we would have them do small experiments in a lab and submit small design assignments to allow them to get a real hands-on feel with the material they are studying. But how do you do this when you have over 40,000 students based in 150 different countries without shipping everyone a complete lab? We approach this challenge as an engineering design problem. We asked ourselves, how can we design experiments for students to do at home, easily, safely, and at little expense? To that end, we came up with this idea.
Excuse me, we? I think you mean me.
Oh, hello, Hannah. I didn't see you there. Ladies and gentlemen, allow me to introduce you our online experimentation specialist, Mrs. Hannah Hypothesis MSc. Hannah, perhaps you would like to explain the next approach.
Of course. We had 2 guiding principles for our experiments. The first was to keep things simple and feasible. If the material could not be found in Jillian's kitchen, garage, or craft cupboard, or easily bought in a supermarket, we didn't use it. We did not want our learners to have to spend a lot of money, and we wanted to show that learning engineering principles doesn't have to be expensive or take place in a lab. Our second principle was that we also wanted students to become familiar with using the scientific method when experimenting. We wanted them to go through the process of making an observation and asking a question, then proposing a hypothesis and designing an experiment, then carry it out, analyze the data, and subsequently accept or reject that hypothesis. So to give some examples, to get a feel of the challenges in the casting process of metals and plastics, we had students experiment with reshaping chocolates by melting down chocolate and pouring it into a mold. And to understand and experience the influences of the environment on materials, our students put an egg into white wine vinegar and observed changes over time. And one of my favorites, to illustrate the principles of different safety design philosophies, we experimented with Lego toy building bricks. The development of safety design philosophies over the years has been critical to keeping aviation safe. But when we use terms such as safe life or fail-safe, or say that loads are transferred from a failed component to a redundant part of the structure, what does that actually look like? My friend, Leah Lego, is a pilot, and she's going to help me demonstrate the differences between safe life and fail-safe design philosophies. She's building herself a new plane from scratch, and she is going to join the rear part of one wing using a safe life design, and the other with a fail-safe design. First, most of the fuselage still has to be built, and then it's onto the wings. On the left wing, there is a single orange block which will be connecting the rear piece. This is the safe life design. And on the right wing, 3 smaller blocks are placed in the same area. This is the fail-safe design. And now for the final assembly and finishing touches, a quick inspection, and last but not least, the propeller installation. Now let's take a look at how each wing fares, starting with the safe life design. Everything seems to go okay for the first several flights, but one day she encounters a gust of wind. It overloads the wing structure, causing the orange connector piece to fail. And unfortunately for Leah, she has also lost the rear section of her wing because that was the only attachment point. Definitely not good. Because it was designed for safe life, the part was not intended to fail during its lifetime, and it wasn't able to handle the excess loading from the gust. Now let's see what happens with the fail-safe design of the right wing. Another gust of wind causes an overload, and one of the pieces came loose. But because of the fail-safe design, when the beige middle piece failed, the load that was being taken up by all 3 pieces has now been redistributed to the 2 remaining blue pieces. So lucky for Leah, the wing is still intact and she can land safely to repair her plane. And now that she's back on the ground, Leah's thinking it might be a good idea to replace the safe life design with a fail-safe one. Fortunately, it's a pretty easy fix. And with that, she's ready to get back to the skies. These experiments were very well received by our learners, both young and old. And after they were done experimenting, we checked their conceptual understanding by asking self-assessment questions to give our learners confidence. But that's more Jillian's field. I need to go back to the lab to cook up some more experiments. As always, it was nice talking to you.
Bye, Hannah. Thanks. So next to having our participants do experiments, we also wanted to have our learners do some qualitative designing. This is why we chose to examine our MOOC learners not only with an exam, but also by asking them to do a design assignment for each module. This required learners to do some research, make design choices, sketch their ideas, and upload them. However, with more than 40,000 learners, we would never be able to correct all assignments ourselves. Hence, students were asked to self-assess or peer-assess these assignments, in which we experienced that students were much harsher on themselves than we would have ever been. An example of such a design assignment you can see here. We asked our students to create a qualitative material design of a combined bulkhead and firewall for a small 2-seater aircraft. It was up to the students to decide if they wanted their aircraft to have a pressurized fuselage or not. Their description of the design was to include answers to issues such as the type of aircraft that they chose and whether it had a pressurized or unpressurized fuselage, what the difference is between a firewall and a bulkhead, and what the consequences are for their design, which requirements a combined design must meet, what materials they should use to make this bulkhead firewall combination, and what shape would this bulkhead firewall have. Also, what manufacturing processes would they choose to manufacture this bulkhead or firewall combination. After submission, learners were provided with a qualitative scoring rubric to assess their answers. As you can see from all this, it is possible to create an active learning experience for students in a distant learning environment using an online platform as a home base instead of a video platform. I can hear you think that's all going to be very expensive, require lots of expertise and very time consuming. Honestly, we found that this does not need to be expensive for you to create nor for students to do. We shot most of the experiment footage on a mobile phone, which you could also ask your students to do if you want them to report back. In terms of video effort, I found learning to edit videos surprisingly easy, and we used the editing software provided by the university. Any verbal instructions to our instruction videos were edited using a lapel mic bought online for a few euros. My total outlay for my at-home studio that was also used making this video has been less than 100 euros. Most experiments never cost more than a few euros in supplies. We ensured all required resources for research were easily available on the web using predominantly open access and public domain sources to maximize accessibility. Our golden tips to successfully implement active learning elements in distance learning are: 1. Keep it simple when designing experiments. You're only illustrating a principle. 2. Are the instructions for the assignments and experiments detailed and specific enough for students to do them on their own without help? 3. Are the experiments feasible and safe to do at home? Would you be able or allowed to do them in your home? And finally, if you can, use senior students to beta test your assignments and experiments, if you have time, to ensure their feasibility. To get inspiration, we looked for easily available common life examples to replace our materials and lab equipment. There are many measuring tools available as smartphone apps these days, but we also use simple offline objects as tools. For instance, if you want students to test the structural strength of a material, they could use packs of rice or flour as weight. We generally came up with our ideas in brainstorm sessions, looking at existing online resources, and also we had contributions from our senior students and at times even our own kids. This part of making the MOOC was probably the most fun for us as a team. We created some 12 experiments in total for our MOOC. If you want to have a look at all the experiments we created, the MOOC is still open for enrollment on edX. Just look up Introduction to Aerospace Structures and Materials on edX.org. With that, I have come to the end of the talk. Which leads me to my challenge to you. Dare to think beyond static video lectures for your courses. Dare to think big, to be creative, and engineer your own pandemic-proof course that students will remember.